Hello and welcome to the second part of section 8.3 where we're going to learn about testing by comparison. There are actually two types of tests for by comparison. The first of which is called direct comparison, which is on this page, page 62. And then there is something called limit comparison, which is on the following page, 63. But for now, let's do direct comparison. So let's consider this series, the sum n equals 1 to infinity, 1 over quantity 2 to the n plus 1. Now, you'll notice that for every n value, the denominator here is ever so slightly bigger than 2 to the n, right? So in fact, we have this relationship right here, that because we have a slightly larger denominator always for each n value, we get a slightly smaller fraction. And so when we add them all up, that's smaller than adding up all of these fractions, just 2 to the n's. We saw this when we were doing comparison of integrals. Remember, larger denominator means smaller fraction, and vice versa. Smaller denominator means larger fraction. Okay, so since we know that the sum of 1 over 2 to the n from starting with n equals 1 and then going to infinity, that sum is actually dead on equal to 1. By direct comparison, this sum must also converge, right? Because it's less than a convergent series. And we saw the same thing with integrals way back in chapter 6. If you were less than a convergent integral, then that integral converged. And if you were bigger than a divergent integral, then that integral diverged. And so the same comparison conclusions are here as well. So because this series is less than a convergent series, it must converge. And so that's really what the comparison test says here. And so for number 1, we can just unpack this as saying less than a convergent series implies convergence. And part 2 here, greater than a divergent series implies divergence. Now you'll notice that the two crossover cases, I'm not even going to write them down, but they don't apply, right? If you're larger than a convergent series, that tells you absolutely nothing. And similarly, if you're less than a divergent series, that tells you absolutely nothing. So only these two apply here. Okay, so series that are good for comparing is if you have essentially a p-series or a geometric series. Those are the big two here. There are others out there, but these are sort of the prototypical ones. So let's look here. Can we determine if this converges or diverges by direct comparison? Well, you'll notice n is starting with 1 and going off to infinity. So n is always a positive integer. And so you'll notice that this denominator, 2n squared plus 4n plus 3, is always greater than or equal to just 2n squared, right? Because I'm always adding something positive to it. So, because I have a bigger denominator, everything else being the same, bigger denominator means I get a less than or equal to symbol, right? And now let's look here. Well, this series is actually a p-series. Can you see which one it is? Would it help if I factored out the 5 halves? Okay, well, this is actually a p-series with p equal to 2, right? This is 5 halves times the sum of 1 over n squared. This we know converges, so multiplying by 5 halves doesn't change that. And now you'll notice this is less than a convergent series, and so it must converge by direct comparison. So you'd show the work like we did above, and then your conclusion after showing the work would be converges by direct comparison, right? Okay, so let's look at this one. All right, so looking at this one, we see, well, notice we have to start with n equals 2, because if we started with n equals 1, we would divide by 0, and that's no good. So we start with n equals 2. Well, can we compare this to something? Well, you'll notice my denominator here is smaller than n, so all other things being the same, So sum n equals 2 to infinity 10 over n. Well, smaller denominator means bigger fractions, right? And now this series right here, I think, is also a very, very special P series, and in fact, it's so special it has its own name. Do we know what this is? This is actually the harmonic series, right? Which diverges. And so now this must diverge by direct comparison because it's bigger than a divergent series. If it helps you to see that this is the harmonic series, just factor out the 10. And the fact that you're starting with 2 as opposed to 1 doesn't change the fact that this diverges. So we would say here diverges by direct comparison. To the harmonic series. But maybe you're starting to see where this strategy of direct comparison is limited. Let's look at the following example here. Notice this I can kind of compare to a geometric series just like way up at the beginning, right? I mean, look at this one, right? It's pretty much the same idea. All other things being the same, you'll notice I have a smaller denominator here. And so smaller denominator means bigger fractions, right? This denominator is smaller than 2n, and so the fractions must be bigger. But here's our limitation. This I know converges. It's a geometric series with ratio equal to 1/2. But being bigger than a geometric series tells you absolutely nothing, right? So direct comparison is inconclusive. And so that's now where we enter the realm of what's known as limit comparison, because your intuition should tell you, well, for large n values, I'm essentially adding up 1 over 2 to the n, right? Subtracting 1 only marginally makes a difference. And so for large n values, I should be doing essentially what I'm doing over here, which adding up values that ultimately do converge. And that is the correct intuition. This series will converge, but we can't show it by direct comparison, right? So here we go. Let me now introduce limit comparison on page 63. So suppose you have two series, both with positive terms, and what you're going to do is essentially find a series. If you're trying to use limit comparison, you're going to find a series that you think the series you have looks like. So for this one here, this series essentially looks like the sum of 1 over 2 to the n, okay? And once you've made your decision, then if you just take the limit of the numbers that you're adding up, so what are known as the summands, so here the summand is 1 over 2 to the n minus 1, here the summand is 1 over 2 to the n. If the limit of the summands comes out to be a positive number, then the series have the same behavior. So they either both converge or both diverge. Okay? So let's actually apply it to this example here. So let's see. What I'll say is the sum n equals 1 to infinity, 1 over 2 to the n minus 1. I'm just going to say looks like the sum of 1 over 2 to the n from n equals 1 to infinity. And so once I've made my decision as to what it looks like, I take the limit, n goes to infinity, of the summands. So 1 over 2 to the n minus 1 over 1 over 2 to the n, which is the limit, n goes to infinity, 2 to the n over 2 to the n minus 1. Right? And we haven't done many like this. You'll notice both the top and bottom go to infinity. So you could say that this is, by L'Hopital's rule, the ratio of the derivatives. That totally works. Now, the way that exponential derivatives work, so pretend that this were like an e to the n, then their derivatives would just be themselves. Well, the same actually holds, but you have to multiply by the natural log of the base. So the derivative of 2 to the n is itself times the natural log of, in this case, 2. And same down here. and the derivative of 1 is 0. Oh, so you notice this is dead on equal to 1, which is a positive number. All you need is that this comes out to be a positive number. And so since sum of 1 over 2 to the n converges, so does sum 1 over 2 to the n minus 1 by LCT. That's a shorthand notation for limit comparison test. Okay, so let's look at this one. You'll notice you can't apply direct comparison. You cannot apply direct comparison. The reasoning is, well, look, sure, you have bigger denominators, but also the numerator is bigger than just 4 to the n. So bigger denominator tells you should be getting smaller fractions, whereas bigger numerator says you should be getting bigger fractions. And so there's a bit of a struggle there. But limit comparison can save us here because we can kind of see that for large n values, this looks like, well, the sum n equals 1 to infinity of just 4 to the n over 3 to the n. And now remember, once you've chosen the sum that you think it looks like, you take the summands and take the limit of their ratio. And so in reality, this limit here is sort of off to the side. Like so. All right, well, this is the limit n goes to infinity. I can flip and multiply the bottom, so I get 1 plus 4 to the n over 1 plus 3 to the n times 3 to the n over 4 to the n. And now I'll use a little bit of ingenuity here. This is 1 plus 4 to the n over 4 to the n times 3 to the n over 1 plus 3 to the n. And moving forward, anytime, oh, sorry, that should be 4 to the n. Anytime you see like a number plus an exponential divided by that same exponential, then the limit is always going to be 1. And this is the reasoning kind of over here, is that you would apply an intermediate L'Hopital's rule to just this, an intermediate L'Hopital's rule to just this, and then the limit of their product is the product of the limits. Well, both the limits are 1. So this is 1 times 1 equals 1. And as long as that limit comes out to be positive, you're good. So therefore, we conclude that since the sum n equals 1 to infinity 4 to the n over 3 to the n, well, what do we think here? Does it converge or diverge? The conclusion is that whatever the behavior of this one, that we said the simpler version looks like, if we decided it converges or diverges, then so does the other one. That's the conclusion by limit comparison. But what do we think? Well, I think that this is actually the sum n equals 1 to infinity of 4/3 to the n, right? And you can peel off a factor of 4/3, and then you get sum 4/3 times 4/3 to the n. Well, r is equal to 4/3. So this diverges because it's a geometric series with ratio r equals 4/3, right? And so that tells you that the geometric series must diverge. Pretty neat, right? All right, moving on. So for this one, the way that you want to do it is kind of treat it like the one above. So get rid of all lower order terms from both the top and bottom. So this one here, this one looks like, well, the sum n equals 1 to infinity of n squared over 3n to the 4th. And by lower order terms, I mean if you have a polynomial, just keep the highest power, right? So here I'm just going to keep the highest power from the top, which is n squared, highest power from the bottom, which is 3n to the 4th, okay? But this simplifies. This is the sum n equals 1 to infinity of, I don't know, how about 1 over 3n squared? And so here I take the summand, 1 over 3n squared. and limit compare it to this summand here. So I get limit n goes to infinity, n squared minus 1 over 3n to the 4 plus 1 divided by 1 over 3n squared. I can flip and multiply, so this is limit n goes to infinity, n squared minus 1 over 3n to the 4 plus 1 times 3n squared over 1. Right? And now do some distributing here. This is the limit n goes to infinity, 3n to the 4 minus 3n squared all over 3n to the 4 plus 1. And there's a couple ways to compute this limit. I would just observe that we have a rational function, polynomial divided by polynomial. N is going to infinity, and they both have the same highest degree, right? So it's just the ratio of the leading coefficients. You could have also observed that L'Hopital's rule applied a few times here would actually work too. In any case, you're going to get a limit of 1, which is positive. So since the sum 1 over 3n squared from n equals 1 to infinity, now you fill in the answer, so does the sum n squared minus 1 over 3n to the 4 plus 1 by LCT. Well, what does this look like? I think this is a p series with p equal to 2, so I think this converges. P series, p equal to 2. Right? All right. And now finally here, well, what does this look like? There are no terms to sort of eliminate in the numerator, so this is still sum of 1 divided by, and in the denominator I think we can just keep the 2n. And so maybe you're starting to get an intuition for this. This here is the harmonic series, right? It's just 1/2 times the sum of 1 over n, which we know diverges. And it's probably going to work out that when I do the limit comparison test, I'm going to get a positive number as a limit, right? So let's actually just verify that. So let's take the limit of the ratio of the summands. So I'm going to flip and multiply, which is the limit n goes to infinity, 2n over 2n plus 3. Apply L'Hopital's rule, or notice that it's a rational function, n going to infinity, and they have the same degree. They're both degree 1, so it's just the ratio of the leading coefficients, which is 1. And since that number is positive and finite, we say since sum 1 over 2n, notice that's not 2 to the n, it's 2n. So since sum of 1 over 2n, I'm going to say diverges, it's harmonic, right? So does the sum 1 over 2n plus 3 by LCT. All right, that's the end of section 8.3. Just integral and limit comparison tests in this section. In the next section, we get into some more convergence and divergence tests.